kind of review a little bit of what we did, and then we'll go on. So we have got, we went over, let's see, the number of significant figures. So if you had a number like 794,000, 79,000, how many significant figures?
3.
3, perfect. And if we had 8.037, how many significant figures?
4.
4, perfect. Now, if we did, and we did everything in scientific notation, so putting this number in scientific notation, 0.0000780. Okay, scientific notation. I'll let you work through, then we'll.
Oh, you just move it to the right.
Yep. 1, 2,
5
3,
times.
4, 5 times. So 7.80, because this zero is significant, right?
Yes.
Because it comes after decimal point, after digits. They're not leading zeros. So 7.80 times 10 to the 5. And we made this number bigger. So you're making this one smaller. So it's -5. Okay.
Yes.
So just remember that this number has to be between 1 and 10. And this is your number of significant figures right there. So if we did math, let's do 8.37 times 10 to the -10 times 0.0035 divided by 63. Let's go 60. Whoops. 64.8 times 10 to the -3. And 814.75 times 10 to the 5th. All right, let's do that. Give the answer the right number of significant figures. So let's get some of that. My calculator, make sure we get the same number here at 8.37 times 0.0035 divided by 634.8 by 814.75. All right. So what did you end up with?
I got 5.664116,992.
Okay.
And then like some weird like E and -8. I don't know.
That's just exponential -3. You're in sign notation. So it comes out to, well, I got zeros. 1, 2, 3, 4, 5, 6. How did I get 7 zeros? 1, 2, 3, 4, 5, 6. I got 7 zeros. 7 zeros. 5, 6, 6. 4, 1, 1, 7. That's not what you got?
No, I got 5.664.
We're off. Somebody's off. Let's see. So 8.37. I might hit a blind decimal. 8.37 times 0.0035 divided by 634.8 divided by 814.75. That might have been it. 814.7. 814.75. Well, I'm at 814.75. Now I get the same thing.
I did it again and it's still 5.664. And then it goes on.
Did you hit divide on the bottom ones? Not times?
Yes,
Oh, yeah.
divide.
Is there an EE in your answer?
Yes.
Okay, your calculator is sign notation, which means it's 10 to what number does the EE say? Negative what?
-8.
That's the same number. So what your calculator is saying is this is your answer, 5.664117 times 10 to the -8. That's what that EE means in your calculator.
Okay.
It's displaying sign notation. So don't get it wrong just because of that, right? Whenever you've seen EE or E on your calculator, that means 10 to the and that power.
Okay.
So so we got the same answer. So we're using that times 10 to the -8, right? That's 2, 3, 4, 5, 6, 7, 8. Yeah, perfect. All right, and then we do the exponents. We have 10 to the -10 times, we bring the 10 to the 3, because we bring that up, we change the sign, and then 10 to the -5. Again, we brought it up, change the sign. So -10 plus 3 minus 5. So that's -7 minus 12, right? So this is 10 to the -12. So we have 5.664117 times 10 to the, and this is -8, -12 is -20. Does that make sense so far?
How did you get the -20?
Okay, we took our 10 to the -10, 10 to the -3, and 10 to the 5th, and that's it right here. That came out to 10 to the -12, right?
Yeah.
Okay, then 10 to the -12 plus 10 to the -8 comes out 10 to the -20,
Okay.
because we're multiplying by this one right here.
Okay.
So we have 10 to the -8 times 10 to the -12, which gives me 10 to the -20.
Okay. Yes.
Does that make sense?
Yes.
Okay, so how many significant digits can our answer have?
1, 2, 3, 4. 3.
This one has 3. This one has
Yes.
4.
3.
This has 5. This one has 2.
Oh, okay. Yes.
So it's the lowest number of significant figures. We only have 2, right? So
Yes.
5 point, we only have 2, so it goes right there. And that number is greater than 5. So 5.7 times 10 to the -20 is our answer. That make sense?
Yes.
All right. So that's basically what we did on Tuesday. So let's go with, now we're gonna go into, we got significant digits, we've got all that done. All right, now we're gonna start using what's called either dimensional analysis or conversions. So we use our dimension analysis to convert from one unit to another unit. So the thing with conversions is we're never changing the number, we're changing the units. Okay, so the value still stays the same. Like 1 dozen is 12 donuts, right? Same thing. I mean, so one dozen is the exact thing as 12 donuts, whatever we have 12 of. Okay, so we don't have to change anything. So when we're dealing with conversions, there's 2 rules. If you know these 2 rules, you'll always get it right. We're always going to multiply by 1. Okay, that way it won't change our number. Always get times by 1. Because whenever you multiply by 1, you never change your value, right? Stays the same. We multiply 1 and we ensure all units cancel. So if 1's on the top, the next has to be on the bottom, so it cancels. You do those 2 rules, you'll get it right every time. Okay. Let's start with an easy example. Let's start with 3 dozen. Say we have 3 dozen eggs. How many eggs do we have? Now I know you can do it in your head, but that's not the point. You always write down what you start with. We're starting with 3 dozen. Okay. 3 dozen eggs. And We're gonna multiply it. That's how you start every problem. You write down what you're starting with, and then you put your next conversion. Now, dozens on the top, so dozen has to go on the bottom. Okay? And we want to convert that to number of eggs. So to make this unit 1, we have 1 dozen. How many eggs in a dozen?
12.
12. Okay? That's 36 eggs. I know you can do it in your head, but that's how we did it. That's how you did it in your head. You write down what you're starting with. You're starting with 3 dozen. Draw a line, and then dozen on the bottom, so the dozens cancel, and you're left with eggs. And this unit here has to equal 1. 12 eggs equals 1 dozen eggs. It's the exact same thing, right?
Yes.
12 eggs is a dozen eggs. So all we've done is convert dozen into eggs. The value is still the same. 3 dozen is still 36 eggs, but then we want to go 36 eggs. And that's how we do it. That's all there is to exponential analysis. Now, there'll be more than one step. There's metrics involved. There's other conversion steps involved. Just remember, this number has to equal 1. That way we don't change our value. We're only changing the units that we want. Okay?
Yes.
All right. So let's start with converting within, let's see, the metric system. Yeah, let's start in the metric system. So let's convert 37 nanometers into meters. All right. So follow the rules. Right now we're starting with 37 nanometers. We do our times and we draw a line. Now, what do we put on the bottom?
1.
Was that? No,
Would
no.
it
What units? This is nanometers here.
Meters.
So nanometers has to go on the bottom. Now remember our metric tables. Nano is the exact same thing as 10 to the minus 9. That's what nano stands for. So instead of writing n, I can write 10 to the minus 9 meters. Because this here is now equal to 1. Nano meters, the exact same thing as 10 to the minus 9 meters. That's what n stands for. Just like small m stood for 10 to the minus 3, mu stood for 10 to the minus 6. Okay, that's right from the conversion table from our chart. Okay, now make sure everything cancels. Nanometers here, nanometers here. They cancel, we're left with meters. So 37 times 10 to the negative 9 meters. Or you want scientific notation, 3.7. And we made this number smaller, made this one bigger, 10 to the minus 8 meters. Same, it's the exact same answer. If they want a scientific notation, you put it in this form. If they don't say anything about scientific notation, you leave it in the first form. The exact same number. All right, so that's a conversion. You write down what you're starting with, and you do your steps to convert it. Okay, making some kind of sense?
Yes.
Okay, because you do a lot of this in chemistry and a lot of other subjects too. You're always doing conversions, half-lives, things like that. You do in biology. You're always doing conversions. So let's convert. Let's stay within the metric system for a little bit and do two steps now. Let's convert say we did a drug rate and we have 3.87 kilograms or kilos of heroin. And I want to convert that into, let's see how many milligrams there is. Okay, so you want to express, there's 3.87 kilograms, and you want to convert that into milligrams. So you be weighed out. So what's your first step? First step is writing this down. What you're starting with, 3.87 kilograms. Okay. Now I guarantee you they're going to get harder. Okay. This is just the basics. But if you keep using the same rules, you get it right. You can't go anywhere else. So put our line, our time in our line. That's how you start, just like that. Now on the bottom, since there's kilograms on the top, you got to put kilograms on the bottom. Okay. And from kilograms, we can go to grams because we know that K stands for 10 to the third. So now I've converted kilograms into grams. But I can't stop there, right? I got to go into milligrams. So I got to grams. Grams go on the bottom. Milligrams go on top because you want the grams to cancel. And milli is 10 to the minus 3. So each of these is equal to 1. This is how I determine what goes on top, what goes on bottom. That's most students have the biggest problem. They don't know where to put the 10 to the 3 on the top or the bottom. But if you follow the rules, you take this kilograms and it has to go down so it cancels. Then this is grams. So grams has to go on the bottom so they cancel. And you just make sure everything equals 1. If everything equals 1, you're not changing the value. You're only changing the units. Okay, so make sure everything cancels. You got kilograms, you got kilograms, you got grams, you got grams. So all we're left with is milligrams, which is what we want. And you'll notice that K right here is 10 to the 3. So that's 1. You notice that M, little m, is 10 to the negative 3. So that's 1. So this equals 3.87 times 10 to the, remember you bring up the exponent, changes the sign. So 10 to the 6 milligrams. That expresses your answer from kilograms into milligrams. Now you can have, some of the ones I'm going to give you are going to have 5, 6 steps with it. They have to convert to this, convert to that, because we're going to go from English to metric and back and forth that system also. We've done a little bit.
So all you do is add both 3's. And then you said, since it's in the bottom, you change the sign just like significant figures?
Yeah, because whenever, this is 3.87, this is the math part, times 10 to the 3, times or divided by 10 to the negative 3. Okay? Remember, we bring this up, we change the sign. So this becomes 3.87 times 10 to the negative 3 times 10 to the negative 3, which is 3.87 times 10 to the negative 6. Whenever you bring up an exponent, you change the sign.
Okay.
When we're multiplying. And when we multiply exponents, we just add the exponents together. And if it's a division, we bring it up and we just change the sign on it. I changed the sign. Whoops. I wrote those wrong. That's supposed to be positive. I'm sorry. I brought that up wrong. 3.8. Let me do that again. I didn't want to confuse you there. Let me just, this doesn't want to, it's moving too slow. Oh, there we go. Just taking its time crossing things out. All right, one more second here. We'll have all that. All right, so what we had was 3.87 times 10 to the 3rd times 10 to the 3rd, because this gets brought up here and we change its sign. And that comes out to 3.87 times 10 to the 6th, because you just add together when you're multiplying exponents. Does that make sense now?
Yes.
I didn't even put those negative signs in there. You can see how easy it is to make stupid mistakes on exams. And the more you practice, the less stupid mistakes you make.
Yeah.
Okay, so that converts kilograms into milligrams. Let's convert, say we got 873 megagrams, and I convert that into micrograms. Okay. Again, write down what we're starting with. 873 micrograms. Draw your line and your multiplication sign. So on the bottom has to be the unit has to be the same, megagrams. Mega means 10 to the 6 on the metric system. That's all in your data chart. Okay, so mega is 10 to the 6 grams. So instead of writing this big M, I can write 10 to the 6. So that's 1, right? It's like writing 12 eggs over a dozen. It's 1. It's like 60 seconds or 1 minute. It's a conversion factor, but they're both equal to 1. You can always multiply by 1 because you never change the value, you're only changing the units. Because when you multiply by 1, you never change the value of the number. And that's how we can get away with it. So times, that goes to grams. So grams go on the bottom. And on the top, we want to go to micrograms. Now, to make that equal to 1, we have to know what micro means. Micro means 10 to the minus 6. So instead of writing the mu there, we can write 10 to the minus 6. So we've gone from megagrams top, megagrams bottom, grams on top, grams on bottom. And we're left with micrograms, which is what we want. Okay.
Yes.
Then we just do the math. We have everything set up. We have 873 times 10 to the 6 divided by 10 to the negative 6, right? That's what all that is. So we bring this up and change the sign. So we have 873 times 10 to the 6 times 10 to the 6. So it becomes 10 to the 12th. So we brought that negative one up, we changed the sign. And scientific notation, if they want it, would be 8.73, make between 1 and 10, times 10 to the, and I made this one smaller, so I made this one bigger by 2. Okay, does that make sense?
Yes.
All right, so that's the metric system. Now let's do the American system. And let's say we want to convert, let's say we've got, let's say we want to convert a 5.32 mile course. I want to convert that into, say, how many centimeters is that? So I got 5.32 miles. And I want to know how many I know what, whoa. I don't want to wait. That's what I don't want. I don't want to go to metric yet. I want to go miles. I want to go to how many inches that is. We're going to keep it in the American system still. Then we'll start converting between the two. All right. Same rules. We have 5.32 miles. That's what we're starting with. Times. So what goes on the bottom?
Miles.
Miles. And one of the conversions I know off the top of my head is there's 5,280 feet in 1 mile. I mean, those are all the data conversion thing I gave, but I just know that one. Okay. So now I've gone from miles to feet. Now feet, I can go to inches, right?
Yes.
Okay, times, and then feet go on the bottom again. And I want to go to inches. Hey, folks. So how many inches are in a foot?
So like, I forgot.
12, right? 12 inches make up 1 foot. So what I've done is I've gone from miles to feet into inches, which I wanted. Okay, and I want to make sure every one of these units I have equals 1. There's 5,200 feet in a mile. There's 12 inches in 1 foot. Okay, and then if it's on the top, you multiply, on the bottom, you divide. So our top number is 5.32. And then times 5,280 times 12 equals 337 075.2. Okay. Now that's in inches. Okay, we make sure everything cancels, make sure I'm 5 by 1. But now I got to do significant figures. Now, in dealing with conversion numbers do not count as significant figures. In other words, this says 12 right here. That's not two significant digits. When we have conversion numbers, those are not measured data. Those are exact numbers. It's like you have 37 kids in a classroom. You can't have 37.1 kids in a classroom or 0.2. You can't have fractions of a kid. Okay, so you have those digits are not measured values. The only thing what's significant is our measured value. This is our measured value, that many miles. Conversion values are a standard that are set. There's 5,280 feet exactly in a mile. There's 12 inches exactly in 1 foot. So our conversion numbers don't count towards significant figures, only our measured data. It's just like there's 12 eggs in a dozen, there's 12. It's 12.000, as many zeros as you need. There's exactly 12. So all our conversion numbers, okay, are not significant figures. Those are givens. Okay, those are counting numbers. Does that make sense?
Yes.
Okay, so the only value we use for significant figures, okay, is the measured data that we started with, 5.32. And that one has 3 significant digits. So this answer here has to have 3 significant figures. Okay, so that means we're going to cut it off right there. Now, we can't say 337 because that's not, well, this number is actually 337,075. So the best way to do it, the easiest way to do it is just put in scientific notation. That way you can always put things as significant figures. It just makes it so much easier than adding zeros around everything. That way you don't get confused. So this notation is 3.370752 times 10 to the what? We've taken this decimal and we've moved it 1, 2, 3, 4, 5. So it's times 10 to the 5th. And we made this number smaller. So we have to make that one bigger. So it's times 10 to the 5. So this is the exact same number now in scientific notation, right?
Yes.
Now it's very easy to do 3 digits. You just put a line right here and we have 3.37 because this is less than 5, this number here, times 10 to the 5. Rather than worry about counting zeros and everything else, this is the correct answer in inches. You have to have units. Okay. So whenever you're kind of confused where to put zeros with these and that, if you don't have enough for significant figures, just put in a scientific notation and it's so much easier. Much easier to do it that way. Can you just count 3 of them? Okay.
Yes.
And let's do one more. Then we'll start doing a cross between the two. So let's now go to, let's see what I want to do. Let's do a measurement of time. So let's say we went 1 week. I want to know how many seconds are in 1 week. Okay, so let's convert 1 week into seconds. And we'll write it as 1 point. Let's say we want, well, 1 week, exactly 1 week. So that must be accurate. Okay, so 1 week. This is what we're starting with, right?
Yes.
So all we start with, right? What we're starting with? Draw our multiplication sign, draw our line. So what goes on the bottom?
1 week.
Week goes on the bottom, and I know there's, say, 7 days in 1 week. So I convert that into days. Okay. And from days, I can convert to what? I convert to hours, because I know there's 24 hours in a day. So day has to go on the bottom. 24 hours are in 1 day. From hours, I can go to minutes. I know for every hour, there's 60 minutes. So every 1 hour, I have 60 minutes. Okay. And minutes, I can go to seconds because there's 60 seconds in every minute. So double check. Again, I went from weeks and weeks, days to days, hours to hours, and minutes to minutes. And I'm left with seconds, which is what I want. I want it to be in seconds. Make sure every one of these is 1. This is how you double check everything. If you've got these 2 steps right, you'll never get it wrong. I don't care how long the conversion is, how complicated it is, you can never get it wrong if you always multiply by 1 and then all your units cancel. So 7 days is the exact same thing as 1 week, right?
Yes.
24 hours is the exact same thing as 1 day. 60 minutes is exactly 1 hour, and 60 seconds is exactly 1 minute. So we multiply by the top, divide by the bottom. Everything's on the top in this case. So we have 1 times 7, which is 7. So you have 7 times 24 times 60 times 60. Comes out to 604. 604,800 seconds. And there's no significant figure to this one because 1 week is exactly 1 week, any partial week. Okay, so you can convert months. You can convert like 8.3 months into seconds. We do a lot of these calculations when we start doing half-lives. We divide by the number, convert everything into seconds or days, depending on the half-life of the element being involved. So that's what there is to conversions. So we do conversion with the English system, with the metric system. Now we combine the 2 systems. We convert from English to the metric system. So let's say we did a measurement and we measured in the lab at, say we had a skid mark we're measuring for a crime scene. Skid mark was, let's say we measured in 81.69 yards. That was the length of our skid mark. And we need to send that to a lab for analysis for the speed of the vehicle before it started hitting the brakes. And they need the number in, let's say, millimeters. That's what they need a number in. So we need to convert 81.69 yards into millimeters to send our data in. All right. So same thing we always do. What are we starting with? We're starting.
You know.
Yep, 81.69 yards. Okay, so what goes on the bottom now?
Yards.
Yards, perfect. And let's see, I want to get to, what do I want to get to? I want to go to inches because I know one of the conversions is there's 2.54 centimeters in an inch. So if I can get this in inches, I can go to the metric system. But like I said, there's yards to meters too, and there's feet. And you can do it multiple ways. Let's do this. Let's do this with 2 different ways. Just shows you the same answer. So let's go from yards into feet. There's 3 feet in every yard. Feet go on the bottom and go to inches. And there's 12 inches per foot. So I've gone from yards to feet, feet to inches. 3 feet in the yard, 12 inches in a foot. Now let's go to the metric system. Now we're going from English to the metric system. I know there's 2.54 centimeters per inch. Now, how do you put the 2.5 from the top or bottom? You do it because inches have to go on the bottom because they have to cancel. And we know that 1 inch is the exact same thing as 2.54 centimeters. And centimeters, I have to go to millimeters. So here's centimeters. I go to meters. Centi is 10 to the minus 2. That's from the metric table. And then I go from I want to go from meters. I'm getting ahead of myself. Okay. We want meters on the bottom and we want millimeters on top. That's what we want to end up with. And milli is 10 to the minus 3. All right. Like I said, it's a lot of steps, but double check everything. Go through yards to yards, feet to feet, inches on top, inches on the bottom, centimeters on the top, centimeters on the bottom, meters on the top, meters on the bottom. We're left with millimeters. And make sure each one of these conversions is equal to 1. There's 3 feet in 1 yard. There's 12 inches in 1 foot. There's 2.54 centimeters in an inch. There's 10 to the minus 2 meters in a centimeter. Centi's 10 to the minus 2, exact same thing. And milli is 10 to the minus 3. So all those are right. And then we just multiply together. Multiply the top, divide by the bottom. So let's save. Usually what I do is I save the exponents to last. So here's my exponents. And then we do all the numbers. So 81.69. I do this right. 81.69 times 3 times 12 times 2.54 equals 7,469. 7,469, 7,336. And this is times 10 to the minus 2 times 10 to the third. Remember, we bring that as negative 3 up, it changes the sign. So this becomes 7469.7336 times 10 to the 1. Okay, because minus 2 and 3 added together is 1. So let's convert this into scientific notation. Let's put this 7.4697336. And I move the decimal 1, 2, 3 places. So it's times 10. I had 10 to the 1 to start with. I moved to 3 places. I made this smaller. I got to make this one bigger. 10 to the 3. 3. Okay. 10 to the 1 and 10 to the 3. It's 10 to the 4 millimeters. Now we do significant figures. How many significant figures can our answer have?
Is it 1?
It's going to be 4. Remember, the conversion numbers don't count.
Okay.
The only one that counts is the measured data. Those are the ones that's only significant because we only measure to a specific amount. Conversion numbers are exact numbers, like counting numbers.
So you said how many? 4?
4, 81.69. There's 4 specific digits here.
Yes.
So that would be 1, 2, 3. It would be right here. It would be 4. Okay, so this number is greater than 5. So that 9 rounds up to a 10. So this becomes 7.470. 69 went to 70 times 10 to the 4th millimeters. And that would be the correct answer. Right, because this is bigger here. So this round that 9 up to 10. So that added 10 was, that made the 7 a 0 and made the 6 a 7.
So where it says like when we first didn't do when it's like 7.46 and then it goes on and then you put 10 to the 4,
right?
It's because like you already like knew that it had to be 4 figures.
Well, no, I this is the number we got. This was our answer.
Yes.
And then we have to add in these exponents. We didn't add them in yet.
Okay.
So this was. Yeah, so this was blah, blah, blah. The significant figures were 10 to the minus 2. And then we change the sign of the other one from and 10 to the 3. That become 10 to the 1. That's where this came from.
Yes.
That's where 3 and our 2.
Yes. I got
Okay.
that.
Okay, and then I move the decimal point 1. The number color I can see here. Purple. I moved the decimal point 1, 2, 3 places. I moved it to here. Okay, so I made the number smaller. I make this one bigger by 3. So I had 10 to the 1,
Oh, okay.
10 to 3 equals 10 to the 4th. That's where the 4 came from.
Okay.
Does that make sense?
Yes.
Okay. And let's just do it a different way to show it would still work. If I knew that, let's start with 81.69 yards. And let's go to feet. Let's take this in. There's 3 feet in a yard, same as before. And now let's convert feet into meters. So I know there's 3.28 feet per meter. So feet go on the bottom. And then meters go on top. And there's 3.28 feet in a meter. So now the number's on the bottom. Okay, so it cancels. Okay. And in meters, I can go to millimeters, which is what I want, right? And milli is 10 to the minus 3. That's the exact same thing I did on top. Okay, make sure you cancel. The yards went to yards, feet went to feet, meters went to meters. There's 3 feet in the yard, there's 3.28 feet in a meter, and there's 10 to the minus 3 millimeters, 10 to the minus 3 meters in a millimeter. Okay. Most mistakes students make is they put the 3.28 on top when it's not. You have to make sure these equal 1. 3.28 feet is 1 meter. 3 feet is 1 yard. 10 to the minus 3 meters is 1 millimeter. So they're all equal to 1. Double check that, double check units cancel, and you can't go wrong. So again, do the math on this one. It comes out to 81.69 times 3 divided by 3.28 equals 74.716, 46, etc. And this is be times 10 to the 3rd. Because there's -3, you move this -3 up, becomes 10 to the 3rd. So we move this over, it becomes 7.471 or 7.472, actually round it up to 4. Okay. Ah. Come on, computer. 7.472 times 10 to the, I move this one place to the left. Let's make this one, make this bigger, 10 to the 4th millimeters. So that's the answer, doing it this way, 7.472, 7.470. And just basically the same number from consistency there. Okay, so either way we do it, we still get the same answer. Okay, so there's multiple ways of doing these things. There is no one right way. It's where you feel comfortable doing it. So, and you can see they can be quite complicated. And we're still making more than that yet still. So we can do top and bottom, but let's do another one. Let's do, say we measured Say, we can say we're 128 pounds. I want to know how many grams. 128 pounds is. Okay, so I want to convert pounds into grams. So we're starting with 128 pounds. Always start the same way. Okay, so what has to go on the bottom now?
Pounds.
Pounds, perfect. And one of the conversions I know is there's 2.205 pounds per kilogram. So 1 kilogram is the exact same thing as 2.205 pounds. Okay, like I said, those are just ones that are on top of my head, but they're all in that data pack I gave you. All the conversions you'll need for this whole thing are in that data packet. Now I got kilograms. So kilograms go on the bottom, and K is the exact same thing as 10 to the 3. So instead of writing K, I can write 10 to the 3rd. So make sure each one of these is equal to 1. 1 kilogram is 2.205 pounds. 10 to the 3rd grams is 1 kilogram. Make sure your units cancel. Pounds, pounds, kilograms, kilograms, top and bottom. We're left with grams, which is what we want. So then doing the math, we start with 128. And where's my calculator go? There it is. So 128 divided by 2.205 times, well, we'll do that. We'll do the exponents after that. So 128 divided by 2.205 comes out to 58.04988. 0.498866. Okay. And then we got our exponent, which is 10 to the 3rd. So times 10 to the 3rd. And how many significant figures can that number have?
3.
3. That has 3 significant digits. So it's going to be 58. When I go this far. So 58.0 times 10 to the 3rd. Or if we have that sign notation, 5.80 times 10 to the, and we moved the decimal place 1. We made it smaller, so we made this one bigger by 1. 10 to the 4th grams. Okay. So it's 5.80, these are digits, times 10 to the 4th grams. Okay, so that converts basically from metric into English or English back into metric. So let's do one more here. And let's do, say, running a 5.00. Say we're running a 5K race, 5.00 kilometers. A 5K race is how many miles?
3 point something.
Okay, 3 point what?
Is it 3.1? Something like that?
Could be, let's figure it out. Let's do a I mean, you could do that, you know, you can look up kilometers a mile, or stuff I know is I have 5.00 kilometers. And kilometers go on the bottom, and kilo is 10 to the 3 meters. Okay, now I'm in meters. I know how many, there's 3.28 feet in a meter. So 3.28 feet per meter. And I know there's 5,280 feet in a mile. Okay, those are just conversion numbers I know off the top of my head. So I don't know the exact one for kilometers to miles, but if you look it up, it's just one step. But you just make sure everything cancels. You make sure your kilometers top, kilometers bottom, meters top, meters bottom, feet top, feet bottom. Then you make sure each unit that you converted is equal to 1. K is 10 to the 3rd. So that's the exact same thing. 3.28 feet is in 1 meter. And 1 mile has 5,280 feet. Then you do the math. You multiply by the top, divide by the bottom. So we end up with 5 times 3.28 divided by 5,280 equals that. So it comes out to 0.003106 times 10 to the 3rd. So move this decimal point over 1, 2, 3 places. It's 3.106. Okay. .106 miles. And we want to go to three significant digits. So it's 3.11 miles. So 5K, like you said, is about 3.11 miles when you do the conversions. And there's multiple ways of doing it. I could have gone to inches to centimeters, then back up to miles. Okay, or you could have just gone like this 0.6 something miles per kilometer. I think that's what it is. But a 5K race is actually 3.1 miles, roughly. Okay, and that's conversions. You'll be doing that all through chemistry and all through a lot of other classes too. There's 2 rules. Multiply by 1, and always make sure your units cancel. On the top one goes to the bottom of the next one. Okay, and we got one more kind of curveball to throw in here. Let's do top and bottom. So let's convert. Say you got a car. Say you want to sell you a car that can travel at 5,328 centimeters per second. You want to convert that, say they're trying to sell you a car that can travel 5,2 centimeters per second, saying that's pretty fast. So we want to convert that into miles per hour. So we know what it is, because I have no idea what centimeters per second means. So I want to go to miles per hour. So now we're starting with 2 numbers. We're starting, well, a top and a bottom number. We're starting with 5,328 centimeters per second. So we got to convert the top number, centimeters, into miles. We got to convert the bottom number, seconds, into hours. Okay, so now I got 2 things to deal with here. So just gonna be very careful in setting these up because it's easy to make mistakes. Okay, so let's set up. Let's do the top one first. So let's do centimeters on the bottom. And centi is, instead of writing C, I can write 10 to the -2 meters. So now we got meters. I want to eventually get that into miles. So you got to go into the English system now. So I know there's 3.28 feet in a meter. So the meters go on the bottom. Then 3.28 feet. And on the bottom, we go to feet. We know there's 5,280 feet in a mile. Okay, I've got my top number in miles now. This is what I want. Okay. So the top number is done. Now let's go to the bottom number. Because if we look, we've got centimeters, centimeters, meters to meters, feet to feet. They all cancel, we're left with miles. So now we'll start with the bottom number. Now, when we do with the bottom number, you have to be really careful because now we're doing the exact opposite we normally do. It's the same things, we just have to do it upside down now. So seconds has to go on the top because seconds are on the bottom. Seconds have to go on the top to cancel. And seconds, I want to go to minutes. And how to make that equal to 1? I know there's 60 seconds in 1 minute. Okay. Now I know minutes are on the bottom, so minutes go on top. And then hours. I know there's 60 minutes in an hour. So now I've converted seconds, minutes, I'm left with hours on the bottom. So now I've got miles per hour, which is what I wanted. So we just do the numbers. It was on the bottom, you divide, on the top, you multiply. So we have 5,000. We'll just say the exponent to the last. 5,328. And then times 3.28. That's on the top. Divided by, it's on the bottom, 5,280. Times 60 times 60. And that comes out to 11,915.3455. Okay, times 10 to the negative 2. That was this exponent right here. So 10 to the negative 2 means the decimal point 2 places to the left. So this comes out to 119.153455 miles per hour. So 119. .1534, and we're good to how many significant digits now?
Would it be 4?
Yep, it would be exactly 4. Perfect. So there's where we draw it. This is 5 or greater. So this rounds up to 119.2 miles per hour. That's decent speed for a car. So he's probably not lying to you. Okay, so any questions on conversions? We can go from metric to metric. We can go from English to English. We can go from metric to English or English to metric. And all you gotta do is remember, write down what you're starting with, and then make sure the units cancel, top and bottom, and make sure every conversion that you do is equal to 1. That way we're just converting the number. We're not changing its value. We're just changing its units. 119.2 miles per hour is the exact same thing as 5,328 centimeters per second. We did not change the number. We only changed the units associated with that. The value of that number is still the same. There's still the same speed, no matter how you measure it. Does that make sense?
Yes.
Cool. All right, let's go on to dimensional analysis. We showed you how to convert all those. We didn't do areas of volume. I think we'll do that later on as it comes across. Miles per yard. All right, temperature conversions. And we have 3 temperatures we're dealing with. Temperatures are degrees Fahrenheit, degrees centigrade, and Kelvin. We can convert between any of those three as we need to. Degrees Fahrenheit is English or American units. Degree centigrade is the rest of the world, the metric system. And Kelvin is the metric system for science. So there's different formulas. I don't want to get these wrong on here. Where's my formulas for? Does the same here. I know centigrade, where's my, you should have it in here somewhere. Hey, boss, what are you doing? Don't have that memorized off the top of my head. Should have it right here. Okay, let me pull up. My data packet here. Let's go through documents, data packet. Because it's already in my data packet, if I can find it. All right. Everything written down here. I don't have all the forms for everything memorized. Here's our conversions. All right. There's two things you want, two formulas you basically need to know. Let's move that up here. All right, so the first one is degree centigrade. Okay, is equal to degrees Fahrenheit minus 32. Okay, divided by 1.8. Okay, now there's parentheses around those, so those have to be done first. If we're doing these numbers, be very careful the parentheses, you're going to see those. Okay, because we'll show you exactly how that works in a second. And the other formula is Kelvin is equal to degree centigrade plus 273.15. With those two formulas, and again, they're in the data package. I've accessed those anytime you need it. You can convert between any of those three values. Okay, so let's say we have, let's say you're in Ireland and they tell you the temperature is 4.3 degrees centigrade. What is that in Fahrenheit? So let's use our formula. We have degree centigrade. Okay, so this calculates here. Degree centigrade. Now I'm given degree centigrade. So I'll rearrange that to solve for degrees Fahrenheit. I can rearrange that by taking I'll have that formula, 1.8 degrees centigrade, 1.8 times degrees centigrade equals Fahrenheit minus 32. So 1.8 degrees centigrade plus 32 equals my degree Fahrenheit. I just kind of rearrange that algebraically. I multiplied 1.8 to both sides, and I added 32 to both sides to Fahrenheit by itself. Does that make sense?
Yes.
Okay, just rearrange it. So my degrees Fahrenheit is equal to 1.8 times my degrees and degrees centigrade, which is 4.3 plus 32. So I take my calculator and I will do 1.8 times 4.3. Okay, and then plus 32. That equals 39.7 degrees Fahrenheit. Okay, so 44.3 degrees centigrade is equal to 39.7 degrees Fahrenheit. And let's do 1.8 times 4. Okay. Now let's do another one. Let's convert from Fahrenheit, okay, into centigrade. So say we got, say it's 29 palms, say it's 128 degrees Fahrenheit. I don't know how much that is in degrees centigrade. So I know my degree centigrade is equal to my degrees Fahrenheit, which is 128, minus 32, divided by 1.8. Now, if you took on the calculator and said 128 minus 32 divided by 1.8, you would get it wrong. Because there's parentheses here. You have to do that one first. Because the order of operations on a calculator is to do multiplication and division and then adding and subtracting. So it would have taken the 32 divided by 1.28 and then subtracted that from 128. So what you're about to do in a calculator, when you have parentheses, is do 128 minus 32, and then hit equals. That gives you a value. Then take that and hit divide by 1.8. Make sure to hit the equal sign in between there. And then it comes out to 53.3 degrees centigrade. Okay, so in this parentheses, do the calculation inside the parentheses, and you hit your equal value, so you get a value, and then divide by the 1.8. So 128 minus 32 equals, divide 1.8 equals 53.3. You have to hit that equal sign in there because of the parentheses. Oops, I lost my calculator. Does that make sense?
Yeah.
Okay. So that comes out. Now let's go from Fahrenheit into Kelvin. So let's say we've got temperature in the lab, and we're running an experiment. We're heating it with boiled water, say the temperature under pressure, let's do 275.8 degrees Fahrenheit. Okay, I want to convert that into Kelvin. Now, you have to go from, you can't go directly from Fahrenheit to Kelvin. You can go from Fahrenheit to centigrade, centigrade to Kelvin. Because our formula was degrees, Kelvin's equal to degrees centigrade plus 270.15. So we go from Fahrenheit to centigrade first. So my Fahrenheit is equal to, let's go back. Fahrenheit is equal to, I'm going to do it, 1.8 centigrade plus 32. 1.8 degrees centigrade plus 32. Okay, so 1.8 times my degrees. Oh, we'll do it backwards. Hold on. I want to go for, I have Fahrenheit. I want to do degrees centigrade. Sorry about that. I'm converting Fahrenheit to centigrade first. So I want to go to degrees centigrade, and my degrees centigrade is Fahrenheit minus 32 divided by 1.8. My degrees Fahrenheit minus 32 divided by 1.8. Now, my degrees Fahrenheit is 275.8 minus 32 divided by 1.8. You do the math, do the parentheses first. Where am I at? Lost my calculator. There we go. So we do 275.8 minus 32 equals, get the value, then divide that value by 1.8 equals 135.4 degrees centigrade. Okay, so now I got degrees centigrade. Now degrees centigrade, we know Kelvin is equal to 273.15 plus our degree centigrade. So our degree centigrade is 135.4 plus 273.15, and that's going to come out to our degrees Kelvin. So again, 135.4 plus 273.15 comes out to 408.6, rounded up. And that is in Kelvin. The density of the object is how condensed the mass is of it. Okay, what volume it occupies. So the formula for density is equal to mass divided by volume. So you have three variables. If you're given any two of the variables, you can solve for the third. Okay. So density is mass over volume. So rearranging that, you can know that mass is equal to density times volume. Just rearranging that. Or volume is equal to mass divided by density. So you can rearrange those so you can solve, you can find density, you can find mass, or you can find volume, depending what you're given. As long as you're given two of the three variables, you can solve for the other one. Density is usually expressed as grams per milliliter. That's mass divided by the volume. There's multiple ways to calculate the volume of something. You can measure it and convert it that way. You can put it in water. Well, the common way we measure volume is to take a graduated cylinder. Graduated cylinder is a tube that has markings across it. Say that's 10 milliliters, 20, 30, 40, and 50. That's a graduated cylinder. So if I fill, say I fill this up to 30 milliliters, and I dumped in, say we dump in a bullet, an object, something like that, we put it inside of here. The water rises to 38 milliliters. So we've gone from 30 milliliters to 38 milliliters. Okay. The volume is 8 milliliters. Okay. That's how much volume it took up in the water. That's one way of measuring volume. Or we can measure it with by length times width times height to get volume too. But volume has 3 measurement units of it. So if we're given the volume of something, we can find its density. Say the volume is, let's keep our same object. Let's keep that. Say the volume that displaced the water was 8.00 milliliters. Okay. Let's say we take that object out and weigh it. We find the mass of this object. We weigh it on a scale. A balance beam is, say, 81.3 grams. We know the density. The density is equal to mass divided by volume. So the mass is 81.3 grams. The density is 8.00 milliliters. Density is usually grams per milliliter. Okay, so we have 81.3. Divided by 8 comes out to be 10.2 rounded up grams per milliliter. That tells you the density of that object. Now, knowing the density, you can look it up on a table of different iron ores, different minerals, whatever it is, and you can, if you know it's an element or you know it's a certain type of ore, you can tell what type it is by its density. Because different things have different densities. Gold is a lot different density than silver, iron, or copper. Okay, so you can calculate different things by their densities. Now, we do some examples with that. I have to figure those out in advance. Let's say we have a, okay. All right, so let's say we have a, mass of copper. Okay, copper wiring. Okay, we say we have, copper has a density of 8.96. Density of copper is 8.96 grams per milliliter. Okay. And let's say we have a graduated cylinder again, and we put it in, we have 100 milliliters, we have 50.5 milliliters of water in a graduated cylinder. We dump that copper, okay, into the cylinder, and it raises up. It goes from 50.5 millimeters to 62.3 milliliters in our graduated cylinder. What's the mass of copper that we have? Remember, density equals mass over volume. And we're looking for mass. Mass equals density times volume. We know the density is 8.96 grams per milliliter. Okay. We know the volume is what? The volume is how much it's displaced from the water, how much it rose. So it's 62.3, that's what it rose up to, minus 50.5 where we started. That comes out to 62.3. 11.8 milliliters was how much the water was pushed up. Okay, so we know the volume is 11.8 milliliters. Milliliters cancel, and we're left with grams. So 8.96 times 11.8. Oops, that's 88. 8.96 times 11.8 comes out to 106 grams of copper. So we know we've got 106 grams of copper. Okay. Pretty much straightforward. Does that all make sense?
Yes, sir.
Okay, it's just density is mass over volume. You can rearrange that. If you give one of the, you have to give them two variables to solve for the third. Okay, so that's our density. That takes care of that chapter. Let's go into some of the chemistry stuff. There's basically three types of matter in chemistry. There's solids, liquids, and gases. Okay. A solid has a rigid shape. Okay, and it has a volume. Like an ice cube, a diamond, okay, a bar of copper, a bar of gold. Those are all solids. The pen that you're holding in your hand is a solid. The wall in your room is a solid. Okay? Then you have liquids. Liquids have a definite volume, but they take on the shape of the container. So solid has a definite shape and a definite volume. Liquids have a definite volume, but they take on the shape of the container. Okay, so if you pour liquid into an ice cube tray, it's cube. If you pour liquid into a glass, it's more of a cylinder. So liquids take on the shape of the container, but they have a definite volume. Gases take on the shape of the container and the volume of the container. If you put a gas in a 5-liter balloon, it's got a 5-liter volume. If you put it in a 2-liter balloon, it's got a 2-liter volume. So the volume and the shape take on from the container for a gas. Examples of liquid would be like water that you drink. Okay, gasoline. Example of gases, example of oxygen, nitrogen, things like that. So there's solids, liquids, and gases that make up matter. You can have a physical change. You have physical properties and chemical properties. Okay, physical properties and chemical properties. Physical properties are how you would attribute to describing something. Okay. Where we're at, physical properties. So the physical properties is the description of it as it is. It's high, its volume, its mass, its temperature. The chemical properties is how it reacts with something, what it can change into. The physical properties of hydrogen is a gas, very lightweight, odorless, colorless. You mix that with oxygen, it becomes water. That's a chemical property, how it reacts in the presence of oxygen to burn to form water. So you have physical and chemical changes, or so chemical properties of things. Okay. So describe it, the boiling point of alcohol is 78 degrees centigrade. Is that a physical or chemical property?
Physical.
That'd be chemical. That's how it reacts chemically. That's just boiling point. Okay, that'd be a chemical property. Actually, wait, I'm sorry, I'm backed up. You're right. Boiling point's a physical property. I was thinking. Boiling point is a physical property. Okay, you're absolutely right. Okay? It's the property of the physical object of it. Okay. How hard a diamond is that a physical or chemical property?
Physical.
That's physical. Hardness. That describes how the physical of it. Let's go another example. When sugar burns or ferments, reacts with to form alcohol. What is that? A physical or chemical property?
Chemical.
That'd be chemical, like fermentation. That's how it reacts. That'd be a chemical property of it. A metal wire that conducts electricity, physical or chemical?
Chemical.
That'd be physical. It does not change anything. That's how it conducts electricity. How hard it is, whether it conducts electricity, whether it conducts heat, the color, the boiling point, melting point. Those are all physical properties of it. When it reacts in a chemical reaction, then you have a chemical property, like fermentation. When you burn wood into carbon dioxide and water, like in a campfire, that's a chemical property of it, how it reacts with oxygen, how it burns, because you're changing the compound itself. Passing electrical current through it doesn't change the compound itself. Whether it conducts electricity, whether it conducts heat, those are all physical properties. If you take a piece of metal and put it in a fire, in a campfire, you grab the metal, it's hot. It conducts electricity, that's a physical property of it. You do the same thing with plastic, as long as it doesn't melt it, It doesn't conduct like heat like a metal does. Okay, so that'd be a physical property. Chemical properties or chemical change is when it changes the composition of it. Like sugar and oxygen combined to burn to form CO2 and water. Okay? That's a combustion reaction. Carbon and oxygen combine to form CO2. That's a chemical property, how they react. Okay. And we cover everything here. Okay, electrolysis they got. Yeah, they want to talk about elements. Okay, in the periodic table, that's a basic list of all the elements. You can list chemical properties and physical properties of how they react, and we'll learn how they're going to react by predicting their behavior from the periodic table. Okay. So if we have you have different mixtures of things. Like if you have we talked this a little bit, we do the introduction. If you have a glass of pure water, that's a solution, okay? That's H2O. Okay, you can have salt in water. And it disperses evenly. Okay, you can have a mixture of oil and water. Okay, so it's two different things. Those different solutions are what's called either homogeneous or heterogeneous. A homogeneous solution is they're all the same. No matter where you look inside that mixture, it's all the same. A heterogeneous can be different. In other words, if I took a sample here, or sample here of my water, they'd all be the same composition. If I took one here, took one here, took one here, that's all the same composition because the salt's mixed in with the water, that they're soluble with one another. They combine together to form a consistent mass of one thing. Okay, there's no difference between the different areas. Whereas oil and water, if I took a sample up here, or I took a sample here, or I took a sample here, they'd all be different. One would be oil, one would be water, one would be a mixture of oil and water. Okay, that's a heterogeneous solution. Okay? They don't mix together. And you can tell by the different densities, the oil is less dense than water. That's where the oil floats. That's the problem we have with oil spills, like the Exxon Valdez that sunk off the coast, all those 20,000 tons of crude oil. Okay, that oil is an environmental hazard. If the oil was less dense than water, the oil would sink to the bottom and wouldn't cause any problems for the fish or the wildlife. But since it flows on top of the surface, it destroys all the wildlife there on top of the surface and the animals that feed on it. Okay, so since the oil is less dense than water, it floats, and that created the problem. So those are your pure substances or homogeneous or heterogeneous substances. Okay, so let's look at each one, and you're going to find it either a pure substance, a homogeneous mixture, or a heterogeneous mixture. So what is gasoline? Is gasoline a pure substance? It's got like octane in it, it's got hectane in it, it's got different compounds in it, but it's all continuous throughout. So gasoline would be a homogeneous mixture. Okay? Everything's mixed together evenly. If we had a glass and we had rocks or gravel, like a fish tank, and water on top, is this whole thing a heterogeneous, homogeneous mixture or a pure substance? What would that be?
Hetero. I don't know how to say that.
Yep, perfect. Heterogeneous. Because different sample points, different points, different places in it. Okay. Say we have air, the air that you breathe in your room. Is that a pure substance, like only one compound, or is it a homogeneous mixture or a heterogeneous mixture?
Is it
It's homogeneous because the different samples in the room, the air is going to be the same. Okay, but it's not a pure substance because it's composed of oxygen, nitrogen, helium, argon, carbon dioxide. So it's a mixture. So it's a homogeneous mixture. How about a piece of copper metal? Would that be a pure substance, a heterogeneous mixture, or homogeneous mixture?
Would it be a homogeneous mixture?
It'd be a pure substance because that's an element. Copper is an element. If it's only copper, it's just a pure substance. Just like a gold bar. If it's only goes nothing else in there, it's a pure substance. Okay. How about a alloy like silver mounds they put in people's teeth, like your silver fillings? It's a mixture of copper, zinc, silver, mercury, but it's all mixed together. So that's a homogeneous mixture. Okay, even though it's a solid, it's a homogeneous mixture. It's a mixture of different compounds. So that's the difference between a pure substance, which is like an element, or a single compound, like just water, would be a pure substance. Homogeneous mixture, one that mixes throughout, like salt water, or a heterogeneous mixture would be like oil and water, where there's differences in it, or gravel and water, something like that, where there's differences. And that's our mixtures. Let's go on to different things. All right. Let's talk about the elements in the periodic table. So the periodic table is a list of all the elements that we know. Okay. In the periodic table, you'll see things are written either with one letter or with two letters. If they're written with one letter, it's always a capital. Hydrogen, potassium, carbon. It's always a capital letter. If it's written with two letters, it's always a capital letter and a small letter. Iron, Fe, copper, Cu, chlorine, Cl. Okay, helium, He. So, and there's a big difference because if you write Co for cobalt, or you write Co big O, that's carbon monoxide. So, large letter, small letter. See, two capital letters is a compound. So if you're doing an element, it's either uppercase single letter, or it's two letters, uppercase, and the second one is lowercase. It has to be that way. Okay, that's how the periodic table is composed. Those are the symbols for all the different elements. Okay, so if you look at the periodic table, it'll show you, okay, all the different elements that we have, and it's an abbreviation. So if I pull my periodic table here, I don't have one sitting in front of me. Let's pull one up. I got one on my data sheet. That's kind of sideways. Let's see if I can switch that around. I can switch that. Let's see if I can. There you go. I'll be able to see it there later. All right, so if you look at the periodic table, you can see how it's developed, how it's designed into rows and columns. Rows go across, columns go down. Okay. If you look at the periodic table, you'll see, let's kind of go over the different things with it. You'll see like 2/3 of the way across, you'll see a dark line dividing it. Do you see that?
Yes.
Okay, that dark line to the right side of that dark line are nonmetals. To the left side of that dark line are all your metals. So it's divided into metals and nonmetals. Okay. When we're doing reactions, you're either going to have two nonmetals that combine, or a metal and a nonmetal. The metals do not combine with each other in a chemical reaction. So that's why it's important with that. So metals are to the left, nonmetals are to the right, and on the line are what's called metalloids. Means they have properties of both a metal and a nonmetal. These metals have a certain hardness, certain brittleness, conduct electricity, things like that. Nonmetals are a lot of those are in the gas phase. Okay? Like if you look at the different colors, you'll see either a blue or green color on your periodic table, like nitrogen, oxygen, fluorine, neon. Okay? Those are your gases in that color. The solids are the black print. Okay? So there's a lot of information on the periodic table. When we write our compounds, okay, like we want to combine, if you have the formula CO2, that's carbon dioxide. We'll learn how to name those in just a minute. But if you see the CO2, that's one carbon and two oxygens combined together. That's what that does mean. That's what subscript 2 means. If there's no subscript, like we have right there, that's we know it's a 1. Whenever the subscript's a 1, we don't put it. If we had SO3, that means we have 1 sulfur and 3 oxygens forming that compound. Okay. If we had, let's do iron oxide. Okay, that's 1 iron, that's 1 oxygen. If I had, okay, that's 2 irons and 3 oxygens. So the substance determine how many elements are in the compound of each element. I have 2 iron atoms and 3 oxygen atoms inside the compound. Okay. If I had nitrogen and oxygen, okay, how many nitrogen would I have in that compound?
2,
2. And how many oxygen atoms would I have in that compound?
5.
5. Perfect. That's it. That's what it means with your chemical symbols. It's telling you how many are combining together to form that compound. 2 nitrogens are combined with 5 oxygens to form that compound. If we have sugar, that's glucose. That's the sugar our brain works on. We have how many carbon atoms?
6,
How many hydrogen atoms?
12,
And how many oxygen atoms?
6.
Perfect. And that's glucose. That's our sugar. That's what it means when we have those formulas. So you can write a compound. If you want to write a compound that has 4 phosphorus atoms and 6 oxygen atoms, you write 4 phosphorus atoms and 6 oxygen atoms. Okay? And that's how they're distributed. That's how you understand how to write a compound. Now, everything's composed of atoms. Atoms are made up of 3 parts. Every atom is made up of protons. Let me really write it out. Protons, neutrons, and electrons. Okay? So protons, neutrons like to make up each atom. Okay? Protons and neutrons are in the nucleus of the atom. So we have a center part. So at the center of the atom, you have okay. So you have protons and neutrons in the center. Protons have a positive charge, and they weigh what's called 1 AMU. That's their mass. It's called atomic mass units. Okay. So they basically have they have a positive charge, and they have a mass of 1. Neutrons have no charge. They're neutral, and they have a mass of 1. Electrons have a negative charge, and they have a mass of basically 0 AMUs. They don't weigh, they weigh a little bit, but not anything compared to proton, neutron. So protons and neutrons are heavier, they have mass of 1. Electrons have basically no weight. Okay, protons and neutrons make up the nucleus, electrons fly around the outer center of it. So you have, in the center of your atom, you have your nucleus, which is composed of protons plus neutrons. And then the electrons fly around it in different orbits. Okay. Now, when you look at an atom is mostly space. The nucleus is a dense compact in the center. So they've done experiments with Rutherford. They'll shoot a proton beam at this. And most of the time, these go right through. Every once in a while, it'll hit the center of the nucleus and deflect it. So that's how they could tell that most of the atom is space, because you shoot protons at it and most will go right through. Every once in a while, it'll deflect. Okay. So basically, you know what Qualcomm Stadium is, San Diego, the big football stadium?
Yes.
Okay, so picture Qualcomm Stadium. In Qualcomm Stadium, take a P and put it in the center of the football field. That represents the nucleus. Everything else, an entire stadium, represents what the electrons are flying around it. So the whole atom is the size of Qualcomm Stadium, and the nucleus is the size of a P. That's how much space is in an atom. So an atom is almost all space. The nucleus is a very, very small, dense part. Okay, but atoms are mostly space that are made up. All the reactions that occur are how the electrons interact. Okay? Everything interacts to combine these electrons in a way that they're going to be stable. And we'll get into that too. So you have protons, neutrons, and electrons. Okay. Proton has a mass of 1, a charge of, and a plus charge. Neutrons have no charge and a mass of 1. Electrons have a negative charge and a mass of 0 as they fly around the nucleus. So that's what they're composed of. Okay, most of the time, everything balances. In a neutral atom, the number of protons and the number of electrons are the same, because those are the only ones that have charges. So in a neutral atom, the positive charges have to equal the negative charges. Okay, so carbon, if you look on the periodic table for carbon, you see a number 6 above the C, right? You see the number 6?
Yes.
Okay, nitrogen will have a 7, oxygen will have an 8, fluorine will have a 9. That number is the number of protons in the atom. The number of protons determine what element it is. If you have 6 protons, it's carbon. If you have 16 protons, it's sulfur. If you have 12 protons, it's magnesium. So the number of protons determine your element. And the number of protons is written on the periodic table as a number above each symbol. So in a balanced element, my protons equal my electrons, because they're the only thing that have charges. So if I have carbon, if carbon has 6 protons, how many electrons does it have? Okay. If there's 6 protons, there's 6 electrons, because the positive and negative charge have to equal each other. Okay. Look at aluminum. Aluminum has 13 protons. So in a balanced state, if it's a neutral compound, if it's balanced, it will have 13 electrons. So they balance. Okay. Neutrons determine the mass of the element. Electrons do not. So the protons and neutrons determine that. So let's go into, let's do carbon. We do protons, neutrons, and electrons. So carbon has 6 protons, 6 electrons. Now, what makes it the mass of an element is called your atomic mass. Okay? Carbon 12 would have 6 protons and 6 neutrons. That would give you 12. 6 protons and 6 electrons balance it. So the charges have to equal. The only thing that has mass is protons and neutrons. So say we had carbon 13. Carbon always has 6 protons. That's what determines your element. How many neutrons would it have? Carbon 13 would have 7 neutrons, because each one is worth 1, right? So we have 7 neutrons, and protons would be 6. Okay. This is what's called an isotope. An isotope is the same number of protons, different number of neutrons. So it's the same element, but it has a different mass. So same number of protons, different number of neutrons is an isotope. Right? Let's do carbon-14. Carbon-14 is radioactive. That's what we use for carbon dating. Again, the protons have to equal 6, because if it's carbon, the number of protons determine your element. If it's carbon, it has to be 6. How many neutrons would it have? Now it has to total 14. So how many neutrons would it have? It would have to have 8 neutrons. Okay. And how many electrons would it have? It would have 6 electrons, because these have to equal if there's no charge. We're going to charge it in just a second. But if it's neutral, like carbon, those have to equal itself. The sum of protons and neutrons, that sum has to equal what's called the mass number, the weight. Okay, so that's an isotope. Same number of protons, different number of neutrons. Okay, so let's do some other examples. Let's say we have, let me pick somewhere here at table. Let's say I have nickel. And let's make it nickel. Where's my nickel at here? It's had it 28. Nickel, where I can put the mass number there, or I can put a dash. But the upper left-hand corner is your mass number. So how many protons does nickel have? Look at the periodic table. Nickel's in the center. How many protons would it have?
28.
Nickel had 28. Yeah, nickel would have. Oh, that's not the right. That's not what I was looking for. Now, yeah, nickel would have 28 protons. How many electrons would it have if there's no charge?
28.
28. And if it's nickel 56, how many neutrons would it have?
$14.
It would have to be, you'd have to have 28 plus some number equals 56. So it has to be 28. Okay. The only thing that has mass is your protons and neutrons. So if this is nickel 56, okay, means it has to total 56. So the protons are 28, the neutrons have to be the other 28. Does that make sense? Okay, say we had nickel 62. We still have 28 protons. We still have 28 electrons. How many neutrons would we have? It was nickel 62.
$36.
30,
34.
34, right? 12,
Yes.
yeah, 62, 34. Okay. Now, we're going to make a chart here. Let me give one more example. So those are isotopes, same number of protons, different number of neutrons. We also have things called ions. Ions are to the charge. Let's say we had N, nitrogen, and let's say it was nitrogen and nitrogen 14. That's our mass. And let's say -2 charge. Okay, now protons are determined right from the periodic table. There's no changing protons. So look at nitrogen. It has 7 protons, right? You get that from the periodic table. That can never change. If the protons change, then the element changes. Okay, so how many neutrons do we have? We know the total has to be 14 because this is the mass number right here in the top left. So the mass has to equal 14. We have 7 protons. So how many neutrons do we have to equal 14?
7.
7. Okay, and electrons, we have a -2 charge. This we have to think about for a second. So if we had a balanced charge, which means the negative protons and neutrons are equal, it would be 7. There's 2 extra negative charges. Negative charges are electrons. So I have 2 extra electrons. So I normally have 7. So now I have 9. Because that gives me an extra 2, give me 2 negative charges. If it was a positive charge, you'd have less electrons because you're losing a negative charge. Does that make sense?
Yes.
Okay, so I have 7 positive charges. So I have 7 positive charges, 9 negative charges. So +7 minus 9 gives me -2. That balances that charge. Okay, so let's make a chart up here. Try to do things a little bit neater. So let's do protons, neutrons, and electrons. And let's do calcium plus calcium is, let's say that's 42. Okay, let's do neon and 21. Let's do bromine with a negative charge, and that's 69. No, that's a 9. We'll fill in this chart in a second here. And let's do CO +2, 27, 54, 58. Let's do sort of negative ones. Sulfur -2 and 30. All right. Now, with all that information, let's fill in these protons, neutrons, electrons for each element. Okay. So read me the numbers you get for the first one, and then we'll go over each one of these. Just take your time and check each one, and then we'll correct them if we need to. All right. So do the calcium one first, top line. Did you get that yet?
For the protons is 20.
Okay, so protons, you would say 20. Neutrons would be?
Would it be 20 as well, or?
Let's put 20 here. And then how many electrons?
Would it be 18?
18 electrons. Okay. protons are 20 because look at the periodic table, you look at calcium, you see 20 protons. Now the mass number, okay, the number of protons plus neutrons has to be 42. That's this number right up here on the top left. So if this is 20, this would have to be 22 to give you 42. Because remember, electrons have no mass. And the mass number is on the top left of the element. We write it down with that. Okay, and your number of electrons has to be 18. You have 20 positive charges, 18 negative charges. Right, so 20, and you have 20 minus 18 is plus 2. So that's perfect. You see why that has to be 22 though?
Yes.
Okay, next one, neon is 21. Neon 21 would have how many protons?
10.
Neon would have, let's write it all down. And then go back and check it. So 10. How many neutrons?
11.
And how many electrons?
10.
10. So look at the periodic table. We find neon. We have 10 protons. We have 11 neutrons. Give you 21, which is your mass number right here, which is perfect. And it's a balance. There's no charge up here. So there's no charge. It's not ion. So the protons equal the electrons to balance the charge. That's perfect. That is perfect. All right, let's go to bromine. Bromine's on the right-hand side. The third one down, the second column to the right.
35.
Yeah, 35 protons. How many neutrons?
34.
34. How many electrons?
35.
35. Okay, let's look at bromine. Bromine is 35 protons. Yep, that's exactly right. Number of neutrons, 35 protons plus neutrons is 69, which is perfect. And number of electrons. Electron, it is a negative charge here. It's a negative charge right there. Means there's one more electron than there's protons. There's one more negative charge. So if there's 35 protons, there has to be 36 electrons. Does that make sense? Because you have to have a net -1 charge. Okay. All right. Now, cobalt 58 2+. How many protons for cobalt?
27.
27. How many neutrons? It's 50,
31.
31. And how many electrons?
56.
How much?
56.
56?
25.
25. All right, let's check it. Cobalt has 27 protons. Yep. The neutrons has to equal 58, so it's 31. That's perfect. And the electrons have to be 2 less than the protons, give you a +2 charge. Perfect. Got it. And sulfur, -2. How many protons?
16.
16. How many neutrons? Oops.
14.
Put this back to blue. So 16. How many neutrons?
14.
14. And how many electrons?
18.
So sulfur is 16. Yep. And neutrons are going to be 14. That gives you 30. And 18 is 2 minus. Yep. You got it. Perfect. Is that making sense now?
Yes, sir.
Okay. So for any electron, no, any element now, we can identify how many protons, how many neutrons, how many electrons we have. Protons and neutrons make up the center. Electrons fly around on the outside. All chemical reactions are determined by the electrons. Okay. We can't, with a chemical reaction, you cannot create or destroy mass. So we cannot change our number of protons. Okay, our elements cannot change. Now that's chemical reactions. Now nuclear reactions is something completely different. Nuclear reactions, we can change the number of protons. So when they talk about the old times you convert lead into gold, you can't do that. You cannot do that with a chemical reaction. You can do that with the nuclear reaction. The thing is, it's so expensive to do the nuclear reactions, it's not worth converting that into gold. So nuclear reactions are a whole nother story. I think we'll get into some nuclear reactions a little bit later too. Those are fun. But chemical reactions, protons stay the same. They're all determined by your electrons, the outer components. That's what determines your chemistry or chemical reactions. Okay, so atoms are mostly air. Okay, very, very low densities. Electrons fly around it. Protons have a +1 charge and a mass of 1. Neutrons have no charge and a mass of 1. Electrons have no mass and a charge of -1. And that's how we determine all these things from the chart. So for any element I give you, you can determine the protons, neutrons, and electrons. So you can also determine the element. If I tell you, let's see, let's continue this just for a little bit here, just for fun. If I have got 7 protons, 8 electrons, okay, what element is it?
Nitrogen.
Okay, nitrogen. And what's the mass number? What's this number right here, this mass number?
15.
15. It's the protons plus the neutrons. That's right, nitrogen 15. If I had, let's say 30, a mass number of 6, 2 neutrons and a charge of, if I had 28 electrons. All right, now what would I have?
Zinc.
I would have zinc. What's the mass number?
32.
Oh, what that should have been 32, not 62. That's 32. So what's the mass number?
62.
62. That's right. Perfect. And is there any charge on it?
2.
2. Because you have 2 more protons than you do neutrons. So it's +2. Yeah, let's do one more. Let's do let's do 15 protons, 14 neutrons. Let's do 18 electrons. All right, so what's my element?
I can't say it.
Okay, good. What's the letter?
P.
P. P stands for phosphorus, which is fine. And then what's the mass number for phosphorus?
29.
29, perfect. And what is the charge on this phosphorus?
+3.
Not +3,
-3.
-3. There's 3 extra electrons. Electrons have a negative charge. Okay, so now you know an element, which is made of protons, neutrons, and electrons. You know the properties of those and how to determine them. You know an isotope is the, so you need to know isotope and ion. Those are the 2 things we've been dealing with. So you know your element, which is on your table. You know it can compose of protons, neutrons, electrons, and their properties. Okay, you know an isotope is the same number of protons, so it's the same element, different number of neutrons. So same number of protons, different number of neutrons, which means it's the same element, but just with a different mass. And an ion. An ion is an element with a charge. That means there's a different number of protons than electrons. If there's more electrons than protons, it's a negative charge. If there's more protons than electrons, it's a positive charge. Okay,
Yes.
perfect. All right, let's go on to, we did a little bit of the periodic table. Now, if you look at the periodic table, we showed you the different rows, the different columns and all that. The first row, I'm saying, the rows go left to right, columns go top to bottom. Okay. There's a group, you see where it says 1A, 2A? On the top, there'll be a 1A, a 2A, then 3A, 4A, 5A, 6A, 7A, and 8A. So column 1, on the all the way to the left-hand side, those are called your alkali metals. Okay, that's column number 1. Column number 2 is your alkaline earth metals. Okay, those are your first 2 columns of the periodic table. Next, you got it kind of sunk down, going from, do you see where it says SC for scandium? That's in the sunken column right to the right-hand side. It's the first element in the 3rd column. See where it says SC? Okay, going down the first one. Well, let's start with, going down the column, you have hydrogen, you have the H, right? Then Li, then Na, and then K. See where it says K? Now go across, have K, Ca, Sc. Okay, where Sc starts, remember, see, it's between those columns. The area between those columns from Sc all the way to zinc, number 30, those are called your transitional metals. See? So your transitional metals is that group all across there. So going down, the first column is your alkaline metals. The second column is your alkaline earth metals. The columns in that center portion, all those columns from scandium to zinc is your transitional metals. Okay. Then you go back up to where it says boron and aluminum, and we go across from there. And then all the way to the right, you have what's called noble gases. Those are all the way to the right. That's your helium, your neon, argon, krypton, and xenon going down. And then to the left of that, those are your halogens. Those are the only ones that you really need to know. Okay. So going across our table, we got the alkaline metals. We have the alkaline earth metals, got your transitional metals. And transition means there's supposed to be different charges on it before you deal with them. Then you got your halogens, which is group 7, which is fluorine, chlorine, bromine, iodine. And then we have our noble gases. Now, the noble gases are at the end of the periodic table. There's a reason we call them noble gases. Okay. Back in medieval times, nobility was not allowed to interact with the common folk. I mean, that still is today to some extent too. They were too snooty for them. They didn't react with anybody else but not even themselves. So noble gases are stable. There are no reactions to it. Like we have oxygen. Oxygen is O2. Nitrogen is N2. Nitrogen combines with oxygen to nitrous oxide, laughing gas. Okay? They react. The noble gases do not react. You don't have helium combined with oxygen. You don't have argon combined with chlorine or anything else, okay? Noble gases don't react with any other elements or themselves. Every other gas on that periodic table is what's called diatomic. So nitrogen is N2, oxygen is O2, okay? Hydrogen is H2. Everything is what's called diatomic. There's 2 of them in nature. That's how they're found. You never find oxygen by itself. The noble gases are only like noble gases are neon. There is no Ne2. Okay, helium. They don't react with anything, not even themselves. That's what they call noble gases. Okay. So if I told you calcium, what is the group, the family of calcium? What family does that belong to? Family is the column. Find calcium, which is number 20. What family is that?
alkyne earth metals.
Yep, perfect. That's your alkaline earth metals. What is bromine? Bromine is 35.
Would it be halogens
Yep,
or
the halogen. Yeah, perfect. That's exactly what they are. And what is xenon? Number 54.
would they be halogens as well?
No, xenon is and all the way to the right. That's the 8th column. That is your noble gases. Your halogens are in the 7th column. Noble gases are the 8th column.
What was the number of it again?
54. '54 is xenon. Xe.
So it would be a noble gas.
Yeah, because all those, where it says He, helium, neon, argon, krypton, xenon, radium, those are all noble gases. So look at 54. It says Xe.
Yes.
It's just around xenon, but it's Xe is a number for it.
Yes.
So it's 50. If it's in that right, if it's in that last column, right hand side, it is noble gases. Just like we're find argon, 18.
Yes.
That's a noble gas. Chlorine, 17, right next to it. That's a halogen. Remember, it runs in columns up and down. Your families are up and down because every column reacts similarly. What we're going to have as we get further into this is the alkaline metals, the first column, are always going to be +1 when they form an I compound. The alkaline earth metals, the second column, always going to be +2. The third column, boron, aluminum, okay? Are all going to be boron and aluminum are all going to be +3. Then the column with carbon is going to be neutral. And the column with nitrogen is going to be -3. The column with oxygen is going to be -2. The halogens will be -1. And the noble gases don't have any ions. That's what we're going to get to. We're going to get to that in a second. So all the families or all the columns react the same way. They either donate or accept electrons. So the reaction is going to be similar. So if you look at magnesium is going to react in the body the same way as calcium does. Lithium, sodium, potassium, those all act the same. When we do nerve impulses, we study the human body with your nerve impulses. Electricity runs through your body. As nerves travel, they switch sodium and potassium. They're both +1 charges. That's what switches to propagate electrical current through your nervous system because they have similar, they're in the same family. They're going to react the same in the body. Okay, so that's our periodic table. And natural state of elements we went over. Elements, diatomic elements. So all the gases we said are all diatomic. Diatomic means combined by 2. So everything that's either green or blue on your periodic table, some are blue, some are green. Okay, those are all diatomic, except for the noble gases. Those are too snooty. Okay. So in our periodic table, the alkaline metals are always going to be +1. The alkaline earth metals are always going to be +2. The noble gases will have no charges, and the halogens are always going to be -1. Okay, so looking at the periodic table again, the first column. I wish I could draw it on the. Let me see if I can draw a periodic table here real quick, or pull up a periodic table. I can do that later. We can pull that up. So your first column is going to be +1. Second column is going to be +2. Then you have your transitional metals, that big section in the middle. Those are going to vary. those would be either +1, +2, or +3. Okay, those are transition because they're going to vary. Then that next section, that 3A group, where it starts with boron, number 5, and aluminum at 13, that is going to be +3. Then your column that starts with carbon, that's going to be neutral. That's what forms all your organic chemistry. Then your column 5A, which starts with nitrogen, then phosphorus, then arsenic, that's always going to be -3. The oxygen column, family's going to be -2. The halogens are -1, and noble gases are 0. And just so you know, we don't do anything with them, but there's those 2 columns at the bottom of the periodic table. That top column is a lanthanide series, and the bottom column is the actinide series. Okay, those are just pulled out of the periodic table to set down because they have different properties, but we very rarely deal with any of those. All right, we got electrons. I'm going to combine. Let's see how we're going to do this. So when we combine, we're going to use those charges to combine elements. You notice all the metals are positive, the non-metals are negative for the most part. So metals are positive charge, non-metals are a negative charge. There are some exceptions. There's always exceptions to everything, but for the most part, that's how chemistry is. Okay, so your metals are positive, your non-metals are negative. So when a metal and a non-metal combine, they combine by charges. Let me close this drape here real quick. There's sunlight coming in. Okay, let's do this and then we'll call it a day. So we have metals. There's only 2 types of combinations. Metal can combine with a non-metal, and 2 non-metals can combine. Okay, you never get metal combined with metal. It's either metal and non-metal or 2 non-metals. When metal combines with non-metal, it goes by charges. That's what determines how they combine. Okay, non-metals combine by their electrons, which is a little bit different. Okay, they tend to share electrons. Metals and non-metals transfer electrons. Okay, so when a metal combines with a non-metal, that's called an ionic bond. Okay, that's when charges are involved. Okay, when non-metal combines with a non-metal, this is what's called a covalent bond. Okay, examples of metal and non-metal is sodium chloride, calcium chloride, copper oxide. Okay, examples of nonmetals would be oxygen, like O2, carbon dioxide, CO2, N2O5. Those are all these are all. What else do I want? Okay, so these are covalent. These are nonmetals. Oxygen, carbon and oxygen, nitrogen and oxygen, bromine. Those are nonmetals. When your metal and nonmetals combined, these are your ionic bonds, and those combine by charges. These combine by, this side shares electrons, this side is charges that can be determined. Okay, so there's different rules in it. So let's go over the ionic bonds. All right, ionic bonds, we're going to use those charges I told you about to combine. So we have a metal and a non-metal. Let's take sodium and let's take chlorine. That's table salt, sodium chloride. Okay, what's the charge on sodium? Look at the group it's in. What charge would sodium have? Sodium is number 11.
Is it 1?
Perfect, it'd be +1. Sodium is +1. Look at chlorine. Chlorine is number 17. What charge does chlorine have on it?
It's like a weird number. Point
It's
sign.
-1. Okay, remember that? If we look, I need to pull up a periodic table real quick here. Thought I had one on my iPad. Let me see real quick. I know I have a periodic table here I was working with. It's Chem 5. No. Where is my other periodic table? Shoot. Darn, it would have to be there. Okay, let's do it this way. I can come back to this, right? I hope so. Okay, let's share my second monitor here. All right. Can you see the periodic table now?
Yes.
Okay. Can you see my little mouse that moves around on it?
Yes.
Okay. This column here. Okay, right, +1 above it. Okay, this column here. Right, +2 above this column. Okay, these are all transitionals. You go to this column right here, above boron, right, +3. Okay, this current one, right, is 0. It's a neutral charge. Okay, this one, right, -3. -2 for this one. -1 for this one. And 0 again right here. So what we have is +1, +2, skip the transitionals, +3. Then our neutral column with carbon. Then we got -3, -2, -1. And then our noble gases. Okay? So that's where I get my charges from. That's what the charge in the family, that's because of how their electrons are. So if we have sodium and we have chlorine, sodium has what charge? Determined by that column. I had you write the numbers above it.
One.
Yep, +1. Yep. What charge does chlorine have? Look at the numbers you wrote. Look at the column it's in.
-1.
-1. So when things combine, when elements combine on ionic bonds, these are ionic bonds, metal and non-metal, they combine so the charge is balanced. So they're going to apply sodium and chlorine, one positive charge, one negative charge. So the chemical formula for chlorine, for a table salt, sodium chloride, is NaCl, one Na, one Cl, and the charge is balanced, right? So we get a 0 charge. Let's look at one more, then we'll pick this up again next time here, because there's a lot of information to take in. Let's combine calcium and chlorine. Calcium has what charge? It's number 20.
0.
No, that's carbon. Calcium is number 20.
+2.
+2. Chlorine again is what charge was chlorine?
-1.
-1. Okay, now to combine these, we have to have 1 calcium and we have to have 2 chlorines. That gives us 2 positive charges and 2 negative charges. So calcium chloride is CaCl2. Sodium chloride is NaCl. So you don't know you know how to combine them because of their charges. The charges have to balance with ionic compounds. Okay, let's do one more here. Let's do lithium. Let's do lithium and oxygen. Lithium has what charge? It's number 3.
+1.
+1. Oxygen has what charge? It's number 8.
-2.
-2. So how's lithium and oxygen have to combine? How many lithiums do we need?
2.
Two lithiums and 1 oxygen. So Li2, oh, now you know how to combine charges. Those are ionic compounds. It gets a little trickier, but we'll go over some rules. There's one more thing I wanted to cover. There's a shortcut or an easy way to do it. Let's take, let's see, nitrogen, and let's take magnesium and nitrogen. Okay. Last one, magnesium is what? What's the charge of magnesium? It's number 12.
+2.
Yeah, +2. And what's the charge on nitrogen?
-3.
-3. Easy way to do this. You combine magnesium and nitrogen. It's called crisscross. We take this number and put it here, this number, put it here. So Mg3N2. It's a little secret, a little trick. Because magnesium is +2, right? So we have 3 of them that gives us a total of +6. Nitrogen, we have a total of, that's -3, and -3, 2 of them gives us -6. That balances. But the easy way to do it is just crisscross them. Take the numbers, put it to each other side. And you'll end up with a balanced compound.